So now we're going to go forward and actually study quadratic forms and their properties. And so I'm going to take this off and we'll use this space to talk about a number of the properties of quadratic forms. Before doing that, let me point out something more about this definition of a quadratic form. The definition says that the quadratic form is a function defined in terms of a symmetric matrix. And of course, if I change the matrix in any way, even keeping it symmetric, but just change to a different symmetric matrix, that's going to be a different function. So this says that there's a kind of one-to-one correspondence between pure quadratic functions, the quadratic functions that only second-degree terms, none of those first-degree terms are zero-degree constant terms. There's a one-to-one function between these pure quadratic functions and the symmetric matrix that represents it. So to put it another way, there is a one-to-one correspondence between quadratic forms and symmetric matrices. And what that means is that we not only could, but we do develop a lot of the properties of quadratic forms, the quadratic functions, by developing the corresponding properties of the matrices. So we can study symmetric matrices and determine properties of those matrices that will correspond to useful and important properties of the function. For example, suppose I want to find out whether the quadratic function, the quadratic form, a particular quadratic form for a particular matrix A is convex, like we had over here in R2, not in R1, in R2. I want to find out whether the quadratic form is a convex function. I would try to find that out by figuring out what the matrix A has to look like, what features it has to have to guarantee that the function is convex. Similarly, what the matrix A has to look like, what its features have to be to guarantee it's concave. And remember, we saw a third picture down here, which was neither convex nor concave. And I would want to know what matrices A correspond to the quadratic forms that are neither always positive or always negative, neither convex nor concave. And similar other properties of the function Q can be expressed, analyzed, determined, proved by doing all those things, expressing it, proving it, with the symmetric matrix A that defines the quadratic form. So with that knowledge under our belts, we can now use that knowledge to develop some of the properties of quadratic forms. So over here, let's say for any quadratic form Q of x equals x ax, where by definition, since it's a quadratic form, A is symmetric. Or maybe I should say for all quadratic forms, okay, the following results are going to be true. So let's, first result we've already, I think, mentioned, and that is that the quadratic form's value, remember, these are all real numbers, so this thing is always gives us a real number. It's always going to be in R. Q is mapping from Rn to R. So Q of the zero vector is obviously the number 0. So if I put 0 vector here and 0 vector here, I get 0 in this matrix multiplication. Second, let's note that for any x in Rn and any lambda scalar, it is the case that q of lambda x is not lambda times q of x, it's lambda squared times q of x. Well, that one's pretty easy to prove. Let's just write a little proof down here. I think we can do it in one line here. So we have q of lambda x is lambda x a lambda x. So that's lambda x a lambda x. And that's lambda times x a lambda x. I could put that in parentheses, I suppose. And that's equal to lambda squared x ax. That's it. That's the proof right there. So here we have q of lambda x. Here we have lambda squared times q of x. So it follows from the second property here that, well, one thing that follows, of course, is that, and this is true for, let me actually make sure that that's clear here. Let's, didn't erase real well. So for all x in Rn, q of the negative of x is the same as q of x, because the negative of x is minus 1 times x. So I would have minus 1 in here. Q of minus 1 times x is minus 1 squared times q of x. Minus 1 squared is 1. So that follows immediately. Let's look at another, a little more powerful, slightly more complicated property. Let's say for any x bar other than the 0 vector in Rn, let's define, just ad hoc for the moment, this isn't, we're not going to be using this permanently, but for the moment, for this property, let's define lowercase script l of x bar to be the set of all vectors lambda times x bar for lambda in R. So x bar is some vector, not the 0 vector, and L of x bar is all multiples of that, positive or negative multiples. So I've used L because, of course, this is the line through the origin. When lambda is 0, I get the 0 vector, so the 0 vector is in here. So this is the line through the origin that also goes through x bar, and so it's actually the one-dimensional subspace in Rn that contains x bar. Another way of saying that is that it's, in fact, I could have written this as the set of all linear combinations. I probably should have done that. It's the set of all linear combinations of the singleton set x bar, because there's only one vector, so I take linear combinations, they're just going to be multiples of that vector, positive or negative. That would have worked too, because L is the first letter in line. So again, it's the line through x bar and, of course, through the origin, so that it's actually a subspace. So do this, then for all x on that line segment, or in here, okay, it's the case that the sine of q at x is the same as the sine of q at x bar. Okay, so in other words, if I look along the line through the through x bar and through the origin, the the sign of the quadratic form never changes. It's either always positive or it's always negative. And I should add here, this means not the 0 vector itself, because of course it's always the case that q of the 0 vector is 0. So I have to be looking at all the vectors on the line other than the 0 vector. So let's actually now look at an example. Let's take off our things over here, and let's look at an example in R2 and see how this works. Okay, so I'm going to draw the axes here. So let's give ourselves a little bit of room. So here are the axes. Here's x1. Here's x2. And now let me draw a square. It's like a unit square, but it's one unit in each direction centered at the origin. So I'm going to draw a square that goes from, this is plus 1, minus 1, plus 1, minus 1. So this square is going to be like this. Okay? So this is 1, this is 1, this is minus 1, and this is minus 1. So I've drawn the value on the axis inside the square, and now outside the square, what I'm going to do is I'm going to write the number representing the value of a particular quadratic form. And so let's let our quadratic form be this. Let's say q of x1, x2 is x1 squared minus 4 x1, x2. Okay, so let's start figuring out the values along here. Let's notice first of all that if x1 is 0, so we're on the vertical axis, if x1 is 0, then both terms are 0 and the value of the quadratic form is 0. So its value is 0 at the 0 vector, the origin, but it's also value is 0 everywhere along the vertical axis. Trying to keep this off to the side so I don't kind of pollute the pink marker with blue. And so that's a line. It's a line through the origin, through the 0 vector, and through a vector x bar if x bar is that vector, or if x bar is this vector, or any other vector on here. It could be x bar. This is the line through that vector and the 0 vector. And on that line, we have q of x equals 0. Okay, and now I'm going to leave off the q of x. That shouldn't have an equal sign in there. Q of x is 0. I'm going to leave that part off and just put the numbers on here representing the values. So what's happening here at this point? This is 1, 1. So this is 1, this is 1, this is 1. So I've got 1 minus 4, so that's minus 3. So this is, the value is minus 3 here. But it's also true that, I wrote this somewhere, here over here, the value at minus x is the same as at x. So that means the value down here, which is the negative of this vector, has to also be minus 3, as you can check. Let's see what is happening at this vector here, and therefore at this vector here it's negative. So this is where x1 is 1, but x2 is 0. So here I have x1 is 1, x2 is 0, so this term drops out, and I've just got 1. So that means the value of the quadratic form here is 1, and it has to be 1 over here as well. Again, because of 3 over here. What about at these points here? Well, at this point here, I've got 1 and minus 1. So I have 1. 1 times minus 1 is minus 1. So I've got minus 4, minus. So this is 5. and therefore this is 5. Let's do one more that I am going to judiciously select. I'm going to pick now the point right here and call that x bar. Okay, so let's say x bar is the vector 1 in this direction and 1/4 in this direction. All right, so first let's evaluate q at x bar. Let's put this over here. And so q at x bar at 1 1/4. So this is 1. This is 1/4. So this is 1/4 times 4 is 1. So this is 1. And 1 squared is 1. So this is 0. So the value, this is probably not good. Let's put this value down here just to make it clearer. The value here is 0. Just like the value along here is 0, the value here is 0, and therefore the value here is 0, and the value everywhere along the line through either one of those points is x bar, like this. This is L of x bar for that x bar, where L is this, and the value is 0 everywhere along here. So let's just write that over here. Q of x is 0 everywhere on this line, and q of x is 0 everywhere on this line, and q of x is positive down here, and, oh, we didn't figure out what it is here. Let's do that. Come on, we got to be complete here. So here we have 0, 1. The vector is 0 and 1, so that's 0. Oh yeah, what am I saying? Well, of course we did. It's 0. There it is right there. So this is 0. This is 0. Yeah, we already did that. Okay. I guess because I stuck it off on the side, I didn't have it here where I kind of maybe wanted it. So you can kind of see now how things are going, right? You can see that it appears that everything in this region between this line and this line, where we have 0 value, 0 value, here we have 1, here we have 5, everything down here, positive. Q is positive. Strictly positive if we're off the line, it turns out. And correspondingly, because of number 3, everything over here, we have Q of x is positive. This is a positive region. And that leaves us with this region here and this region here, where the values have to be the same according to 3. And here you can see I have 0 here, I have 0 here, and if I go around the border of the square, I have -3 here, and at all these other points it'll be negative as well, as you can check. You can check everything I've said here by looking at other values along here, or even develop a little proof that at every value in here, Q is strictly positive, every value in here, and of course all multiples, I'll just write negative. Q is negative, and everything down here, Q is negative. And so I guess one question we might have is, what does this quadratic form's graph actually look like? The graph is in 3 dimensions. We've drawn several 3-dimensional graphs. Turns out we've drawn the graph of this quadratic form in 3 dimensions, and here it is again. This is the one we put up here a little earlier. That's neither concave everywhere or convex everywhere. It's not concave, it's not convex. It kind of is concave in some directions and convex in other directions. And this is the graph of this quadratic form. And if you look at this carefully for a little while, you can kind of see that there's there's a line in the domain, like this one, along which it appears that the graph is actually just zero, just stays zero. And another line, one of the axes, you can see where, again, you can think of it, in this picture here, you can think of the, in this picture here, you can think of the y-axis, which we'd normally write vertically. You can think of it kind of going through here. So it's, let's say it's positive towards you, and it's negative towards me. And so you can kind of picture with these values what that graph would look like, roughly. And of course, if we draw the three-dimensional diagram, this is what it looks like. So this example does several things. It enables us to see an actual quadratic form that isn't a particular quadratic form, that isn't everywhere concave or convex. It changes its shape as we move through the domain. This example enables us to see what's going on here in this item 4, and for that matter, items 2 and 3 as well. Notice several other things. I guess that is that I can tell everything about this quadratic form by just looking at what it does on this square, because I know that if its value is -3 here, it is negative everywhere along this line. Moreover, I know that if I go out twice as far from 1, 1 to the 2, 2 vector, I go twice as far, its value gets 4 times as big. So if I go out to 2, 2, its value is going to be -12. Down here at -2, -2, value is -12. Go out to 3, 3, value is going to be, let's see, it's going to be 9 times this, it'll be -27, and -27, and so on. And the same for every point on the square. If I want to know, let's turn it around, kind of take the inverse. If I want to know what the value of this quadratic form is at any point in the domain, let's say this one down here, I just call it x bar. I just project back to the origin and see what's the value here. That tells me the value down here because I just multiply by lambda squared times the value here, and I get the value down here. So I can tell everything about this quadratic form by just doing what we just did. I can tell what its values are at specific points. I can tell regions where it's negative, regions where it's always positive, regions, subspaces, lines where it is always 0. And that, of course, works for more than just this square. I could have used the unit circle around here just as well, where it would, the unit circle, in fact, I'll draw that in here in a different color just to make that point. Let me use a not quite so obtrusive color. Let me draw the unit circle in here. This is supposed to be a circle. I'm not doing too bad a job, actually. That's better than I can usually do. So I draw the unit circle in here. And the same thing is true. If I want to know the value at any point, I can just identify its value on the unit circle and then figure how far out here I go. I didn't use the unit circle exactly because the square was a lot easier to identify certain points and then figure out and put the values in here as x1 and x2. It's a little more complicated at these points on the circle. But here, it's easy here because I've got 1 or 0 or -1 at every one of these, every one of the points that I looked at here. So I could use any set S, call it, that is centered at the unit vector, and I would be able to use that set to tell me everything I want to know about any given quadratic form.
Yeah.
Well, it looks to me like this lecture is now starting to run a little bit long. So what we're going to do is we're going to take a break. And so this first part here will be part 1 of our lecture on quadratic forms. And then we'll come back and do a rather short part 2. and then probably a little bit longer part 3.